So our topic for today, and probably for the next lecture as well, is what I'll call it as beyond NP, the polynomial hierarchy. And the polynomial hierarchy is often called PH. Okay, so what is the polynomial hierarchy? And the best way to understand these complexity classes is to think of problems that we're trying to capture. So let me talk about a couple of problems which are natural, interesting, and don't seem to fit. They actually seem to be harder than NP. Let's take a simple one, given that we talked about clique. So recall that clique was this language GK, where G has a clique of size K. Let's look at this language, exact clique, which is very similar, but the largest clique in G has size exactly K. Now recall that we said this is an NP. What about exact clique? Is exact clique in NP? Is exact clique in NP?
Yeah, I mean, the certificate would just be an example of the clique, right?
The certificate will only tell you that there is a clique of size K, but how do you know that there isn't a bigger one?
Oh.
Right? The certificate just says you have a clique of this size, but it doesn't tell you whether there's a bigger clique.
Right, that's true.
Right? What about the certificate of not being? So we might think, okay, maybe it's co-NP. Like maybe it's co-NP. So let's see. Can we design certificates for GK in or not in exact clique? So let's think. Suppose GK is an exact clique. Well, how do we certify that there isn't a larger clique than K? You can give the clique, but how do you know that there isn't something that is larger? The certificate, how is it going to... And this looks a lot like co-NP. Instead, let's just say that GK is not an exact clique. Maybe there's a certificate for this fact. But the problem is there could be two different reasons. Either there exists a clique larger than K. This we could certify. Or all cliques are smaller than K. Do you see that when it's not in the language, there could be two reasons. Either there is a larger clique. The first part seems like NP. Or all cliques are smaller than K. The second part seems like co-NP. So it's almost like a mix of both of these. Right? This looks like NP. This is a certificate that can be checked. And this looks like co-NP because you need something to hold for all. And this is there exists. Does this make sense? Does the language make sense and the challenges in this? Okay. But if you look at this language, there is clearly a relationship with clique. I mean, it's not, it's, and what is that relationship? If there is a procedure that decides clique, the vanilla version, then exact clique can be solved by at most n. It's even better. It's actually at most log n. Log n calls to the procedure. Do you see that? Like if you could, if you can determine the clique, if there is a clique of size at least k, which is technically what this is, then you could just do binary search, or you could even just do linear search over all values of k, and you find where essentially there isn't a clique of size greater than or equal to k, and then, excuse me, you're done. So exact clique can be solved if you could make calls to a procedure that solves clique. Indeed, this used to be called this is called a Turing reduction, which is different from the kinds of reductions we do. But I don't want to necessarily get into Turing reductions, although it's related to this. But I want to make this point really clear, that a procedure to solve clique can be used to solve exact clique. And by used, it can be used sort of at most polynomially many times. So if there was an efficient procedure for clique, there would be an efficient procedure for exact clique. On the other hand, we don't have a reduction in the kinds of ways we do. We don't have a mapping reduction between these. We don't know if a mapping reduction exists. We don't think it exists. Questions? It's a subtle point. Okay. I'm going to now talk about another problem, and this problem actually goes back to the early days of computer science, and indeed the study of computer science as it started arguably in some ways in the the 50s and 60s, which was on circuit generation. And the question was, you could think of circuit design, right? Let's say you have to construct a circuit in silicon. What is, and this really started off with, what is the smallest circuit to, let's say, multiply two numbers, multiply two n-bit integers. And this was the problem, and instead of multiply, you could think of anything. You could think of add, multiply, whatever function, right? What is the smallest circuit to compute some function? Right? And this is a very natural question that was asked. So let me now give you a formulation of this question in terms of languages in the way that we usually do. And let me call this smallest. Instead of circuit, let's use formula, because we've done Boolean formulas. So what is this language? This is all encodings of circuits, so that this is the smallest, the minimal formula that computes a function. So what this means is phi is the smallest formula computing a function, and the smallest is just by encoding size or encoding length, right? Whatever that encoding length is. So we've encoded it in some way. This is the smallest formula. Now this seems that even if you could solve SAT, it's not clear how you would construct the smallest formula. Let me express this in a different way. Let me say what this is for all phi prime, there exists an input x such that if the length of phi prime, if the encoding length is less than the encoding length of phi, then phi of x is not equal to phi prime of x. This is just saying that if phi prime is smaller, then phi is not equal to phi prime. But what does it mean to be not equal? It means that there's some input where they differ. Where there's some input where they differ. This by itself is like a formula. Like once you fix phi and phi prime, this itself is a formula. So you could, even if you could solve SAT, SAT could solve this for you. Given two formulas, you can say, are they the same or not? Right? And SAT can solve that. Does there exist an input where they differ? But even if you could solve SAT, like how do you go over all possible circuits or all possible formulas? Even if we can solve SAT to decide if phi is equal to phi prime, we still need to consider all phi prime. At least in this formulation, you still have to consider what are all the possible circuits and whether there's something that is smaller. So any questions about these problems? Exact clique and smallest formula.
I know that there's some concepts. Maybe this isn't exactly the same, but I know that there's something about like finding the least amount of like theorems to solve like a certain like to prove something. Is that like related to smallest formula? I mean, I suppose this is more about like algorithms, though.
Well, I mean, there is some relation to what's called Kolmogorov Complexity, which is like what is the smallest encoding of the function. And there is a whole, like, that's a lot of that has to deal with like Kolmogorov Complexity, even things in information theory. And here it's a little different, right? It's more like, I mean, okay, they are related at some level, but the way to think of this is just like this is a language, and you want to decide. Like, let's say I give you input. I've constructed a particular circuit to multiply, and I want to see, is this the smallest circuit that multiplies? Is there an algorithm that can determine that? Whenever we talk of languages, we're thinking, is there an algorithm that will decide this language? Does this sort of help? Does this give some clarity to what this is?
Yes, thank you.
I mean, and you've probably seen this during the course. We start with like a problem we'd like to solve, and we try to formulate it in terms of languages, because I think that gives a lot of clarity, and that gives a lot of we can now build on all the formalism of languages. So we design a language which is intimately connected to the problem we're trying to solve, and then try to understand, is the language, what kinds of complexity properties does this language have? And this language seems to be even beyond NP. And it's beyond NP because there are two quantifiers. If there was one quantifier, if there was only a there exists, it's SAT. That's NP. If there was only a for all, that's co-NP. But here you've got both. Now we've seen multiple quantifiers before. We saw quantified Boolean formula, and indeed that is going to have connections with what we're going to discuss. So what I'm now going to do is, let's think of this in terms of oracles. So what is an oracle? So let me instead do it as, let L be a language. P to the L. What this means is it's a polynomial time machine with an L oracle. So what this really means, here's the way to think about it. So here's your machine M. Here's the input X. What it also has is something called the oracle tape. So it can go ahead and write down something here. So let's say it writes down Y here. And then it can ask, is Y an L? And it's going to get an answer. And then you can use that answer in its, or you could assume that the answer will get written at the end or whatever, or it moves to a separate state. One way to think of it, it moves to another state. Like it can basically ask questions. So this is a machine with access to a subroutine that decides L, and here's the important one, in unit time. Meaning that means it does it in one time step. So it has access to a subroutine that can just immediately decide L. And that's an oracle machine. This is called an oracle machine. So P to the L are polynomial time machines with access to an oracle. And this is capturing exact clique. Because if you have access to a clique machine, then you can call that machine n times, or actually log n times, to decide the language. Does the oracle machine make sense? Okay. And well, now that we've done this with P, we can do this with NP. And we can look at NP to the L, which are non-deterministic polynomial time machines with an L oracle. Now, if you think about it, smallest formula is actually in co NP to the SAT. What does this mean? It says when phi is not in smallest formula, there is a certificate that can be polynomially verified with access to a SAT oracle, right? Because in this case, what this means is there exists some phi prime such that phi prime is equal to phi. So this is the certificate, and this requires a SAT oracle. Right? You can always check two formulas, because this, whether two formulas are the same, is basically that's a formula, and it can just evaluate this formula. Does this make sense? Why smallest formula is in co-NP to the SAT. So it's co-NP to the SAT. But we can also switch the parentheses. But questions? All right. And in general, suppose C is a complexity class. Then you can define NP to the C as non-deterministic polynomial time machines with oracles to languages in C. But if you really think about it, for NP, you only need an oracle to a complete problem. It suffices to have an oracle for a C complete problem language. And so what we saw over there can also be written as NP to the NP, or technically this was co-NP to the NP. Okay, co-NP to the NP. It's an NP machine that has access to an oracle that can solve an NP machine. So NP to the NP is actually more powerful than NP. And indeed, this is where the polynomial hierarchy starts. This actually has a name. This is called pi2, and there's a p here. The p is polynomial. This means polynomial. The 2, as we'll see, is the number of alternations. Number of alternations of quantifiers. So this is a bit, and what we're going to study in this lecture and the next one are alternate definitions of these classes to give you a better sense of what this actually means. Any questions at this point? Now, this is quite a bit. There are lots of new definitions here, so please ask me questions to sort of clarify our understanding. What does NP to the NP mean? What does co-NP to the NP mean? What does NP to the C mean? So on and so forth.
So can you have like co NP to the NP, and then and like it in pi 2 equals co to the NP, or co NP to the NP? Is there the other parentheses around the NP as well there? You mean, or
it's basically this.
Okay.
I mean, you mean you could also define it as, is it co-NP sort of to the power NP?
Yeah, right.
Effectively, that would be the same, because the problem is there's no such thing as a co-NP machine. It's really just an NP machine that's flipped.
Right.
So it's better to think of NP to the NP, and then you put the co after that. Right. Co is like complementing a class. So let's think of it as you're defining a class with respect to a kind of Turing machine. In the end, like, all of these things are going to be equivalent, but just, the first time you encounter this, the way to think about it is you've got a particular kind of machine, a polynomial time machine, a log space machine, a non-deterministic log space machine, a non-deterministic polynomial time machine. So you have a very clear definition of what that machine can do, in the sense of a clear sense of what that machine does. What does it mean for the machine to accept? What does it mean to reject? You have these definitions that are laid out. And you have a bound on runtime. Now what you're doing is you're giving this machine additional power. You're saying, you know what, this machine is allowed to query another language just for free. It's like subroutines. What we're trying to understand is, okay, let's just say you could solve SAT. Let's say you can solve SAT. Does that now make everything easy, or are there things that are still going to be hard? And that's really where smallest formula comes in. And this is, I think, where some of the initial discussions of these languages came in. Say, even if we could solve SAT, we still won't be able to determine if this is the smallest circuit for multiplication. Because all the SAT oracle can do is to determine if some other circuit is equal or not. That it can do. But that by itself, is that enough to find the smallest formula? Indeed, like, these things are real problems, because, if any of you, if you ever come across formal methods and verification, a lot of the questions that you have in validating circuits and validating code ends up being of this form. Does there exist a smaller piece of code? Is there a compiler optimization that's possible? Are there going to be bugs in the code under certain circumstances? A lot of these questions are of this form, that even if you could solve SAT, you still can't solve, even if you could solve SAT efficiently, it's still not clear how one would solve these problems. I hope this gives some intuition, some explanation of what's going on here. Because, I can start throwing out the definitions and the theorems at you. But that's not the point. The point is to understand why you would want to study these complexity classes.
Thank you.
Questions? Further questions? All right, so let's continue. I'm going to now give you multiple definitions of the polynomial hierarchy, and we'll see that all of these are equivalent. So I'm going to start with I'll start with definition 1, and this is through Oracle machines. Now, this definition may be a little confusing, so we're going to use another definition for the theorems today, but I want to sort of give you this definition because we've been talking about Oracle machines. So this is an inductive definition. We'll define sigma 1 is NP, and pi 1 is actually just co of sigma 1. So this is co of NP. Sigma I plus 1 of P is an NP machine that has access to an sigma I machine. So it's an NP machine with Oracle access to a sigma I machine, that's sigma I plus 1. And then, of course, pi I plus 1 is just co of sigma I plus 1. Of special significance are usually sigma 2 and pi 2 will often appear. Sigma 2, pi 2, there are even some problems in sigma 3 and pi 3 which appear naturally, and I'll probably have this in the assignment. There's a very common concept in machine learning called the VC dimension, and if you look at what is the sort of the complexity of finding the VC dimension, it ends up falling in like sigma 3. Okay, so this definition can be a little confusing, but again, think of it as you construct this powerful oracle that can solve the smallest circuit. Now what can you do with that oracle with an NP machine? and so on and so forth. So this definition is the Oracle machine definition. I'll give you another definition in terms of certificates, which I think is much more easier to understand. Okay. And we will prove that all of these are equivalent. So I'll do definition 2. And this is sort of the alternating certificate viewpoint. So I'll say L is in sigma I of P if there exists a polytime machine M and a polynomial Q such that, so you'll see this is going to be very similar to the NP and co-NP definitions of certificates. If X is in the language, if and only if there exists a certificate U1 such that for all certificates U2 there exists a U3, so on and so forth up to UI, such that MX U1 U2 up to UI accepts, where all the UIs are at most polynomial sized. So if you only have I being 1, then this is exactly NP. Right? If you removed all of this, then that's NP. You put 2 of them, you get sigma 2. So it means that there exists something such that for all U2, U3, U4, so on and so forth. And of course, we always just define pi I as just sigma I. These complexity classes also appear a lot in database queries, in like what kinds of database queries can be, if you're trying to understand what is the complexity of answering a particular database query, then notions like this come about. And the polynomial hierarchy is just the union over all integers. I should just call this I of all sigma I. That is the polynomial hierarchy. I've given 2 definitions. I have to show that those 2 definitions are equivalent, which I may or may not get to today, because as an intermediate step, we're going to understand complete problems for these, and then that will add a lot of clarity. So if the Oracle machine definition becomes a little confusing, which it can if you try to sort of unravel everything, I think this definition is sort of more easier to understand. Because if you wanted to understand the complement of smallest formula, so let's not look at smallest formula, which is but rather the complement of smallest formula, which means that it is not the smallest formula, then the certificate will be the smaller formula, and for all inputs, the smaller formula computes the same value as the original formula. Right? That's what this machine will do. So this machine will okay, so maybe let me write this down. Let's just look at the complement of smallest formula, which I'll just call it as not smallest formula. Okay? So recall that this is all encodings phi, so that phi is not the smallest formula computing a function. I guess technically I should call this minimal and not smallest. It's like minimal formula. But okay, so what does this mean? What is M going to do? So M is actually going to do something really simple. So M is going to take inputs phi, phi prime, and x, and M accepts if phi of x is equal to phi prime x. So clearly M is polynomial time. Clearly polynomial. This is polynomial time. Okay. So what we can say is phi is in, let me refer to this as L. Phi is in L if and only if there exists a phi prime such that for all x, M phi prime x accepts. Right? Because what this would mean, okay, so I should say accepts this if this happens and phi prime is smaller than phi. Sorry, it should first check this, right? Which check both of them. Right, so first it's going to take something that is smaller, and it's going to say if there exists something that is smaller, then for all x they should be the same, in which case it is not the smallest formula. And therefore L is in sigma 2. Any questions? Questions?
Well, I guess I'm wondering, is the above definition, is that like more of like a reflection of like something else, or is that like what like a first principle sort of definition? Like I'm not sure if that makes sense, but it's like, you know, are we building that definition? You know, because it seems like this whole thing about there exist, you know, this alternation between there exists and then for all. I mean, is that based on, you know, another principle, or is that how we're defining it, and then we're basing all of our other observations off of that?
I guess, you know, to some extent it's a bit of a chicken and egg question whether the first thing to come to mind is the Oracle machine or this viewpoint.
Yeah.
And it turns out that they're equivalent. It turns out they're equivalent. But, you know, the reason I wanted to sort of write it this way is to show you that this natural language sort of has this expression in this form. One way to think of it really is that, you know, we did QBF. So this is like QBF with a finite with a constant number of alternations. And we're going to see that. Okay, so let me now give you yet another definition. And this is almost like a third definition of the polynomial hierarchy. There are actually many definitions. So I'm going to define a language called sigma I sat is a language of formulas phi, where phi is actually going to have what is the best way? Okay, yeah, so I'll just say u1, u2 up to ui. So it has I, you know, I things in it, I inputs, and we'll say that so phi is in, I guess the encoding of phi is in sigma I sat if there exists a u1 so that for all u2, you know, switching I times, switching quantifiers I times ui is equal to 1. Again, if I was equal to 1, then this is just sat. But this is like a switching quantifier version of sat. This is a special case of QBF. It's a special case of QBF. And the specialness is in the I, because it only switches the quantifier I times. So it's only allowing a constant number of switches in the quantifiers. Another way to think of this is if you wanted to think of a game of chess, think of it as we fix the number of moves we can play. So for any move I make a move, I want to make a move so that no matter what you do, I can do something, so that no matter what you do, something happens, but the number of times the quantifier switches is constant. So these are like chess puzzles. If you've seen those chess puzzles where you have to, get checkmate in 3 steps. Not win the entire game. So it's a special case of quantified Boolean formula. Now with all this sort of setup, let's prove our first main theorem, which is that sigma I sat is, you may not be surprised to know that it is complete for the ith level of the polynomial hierarchy, or the ith sigma I, and pi I sat. So I should have said sigma I sat is when it starts with this, and so in pi I sat, it basically starts with a universal. So it's for all u1 there exists u2, so on and so forth. It's just starting at a different point. And if you think about it, it's basically just the negation. Right? It's just the negation of this language. Or I'm sorry, the complement of this language. My apologies. It's the complement of this language which is obtained by basically negating this formula, or by negating this entire condition. And so pi I sat is pi I complete. Questions? Questions at this point?
Can you go back really fast
Sure.
to the definition of pi I sat?
Yes.
Okay, so this formula phi, it's special in that it always equals 1, no matter what, for any of its inputs, or to satisfy it.
No, it says that there exists a u1, so that for all u2 there exists a u3, so that for all u4 there exists a u5.
Right, but the formula, if that's the case, then the formula equals 1.
I mean, no, it's saying that there needs to exist this for the formula to be 1.
Okay, I'm a bit confused about why 1.
Or true. I mean, this is 1 is just true,
okay.
Right?
Oh, I see.
Sorry. It's true.
That clears.
Yeah,
clears
my
things up.
apologies. My apologies. It's true. So let me draw a picture which might help, and then we can come back to this theorem. So we'll come back to this. So this is just saying that just as sat was NP complete, this is like the generalization of the fact that sat is NP complete. Sigma I sat is sigma IP complete. Okay, so what is? Let's think of sat in terms of a tree. So just think of phi u1, u2 up to ui. Okay, so you could imagine that you have different choices for the setting of U1. You can set U1 to whatever you want. Then you set U2, U3, so on and so forth, until you finally set UI. Okay. What is SAT? SAT means that there is a way of going down the tree so that I end up at true. What is sigma I SAT? Sigma I SAT says that there exists a way of going down here so that no matter which path I take down here, there's going to be something down here, so that no matter which one I take down here, there's going to be something down here which takes me to true. So this is like one, in this case there would be 5 quantifier switches. It says there exists a U1 so that no matter what U2 is, there's always a U3 so that no matter what U4 is, there exists a U5 which is going to lead me to true. So this is like a game where we only have I steps. If there was no step, it's a puzzle. I just have to find some path going down the tree. Sudoku, where I just have to find a solution. Now it's some kind of adversarial Sudoku. I place something, but then the adversary is going to try to thwart me by playing something else. But I always have a way of getting out. And no matter what the adversary does, I have a way of getting out, so that it's true. That's what sigma I is. Think of it as a game where you'll have a few iterations. And that's why sigma 2 and pi 2 appear a lot, where you have sort of attacker-defender situations where it's like, attacker plays once and the defender has to defend. So it's 2. So sigma 2 and pi 2 tend to appear a lot in the literature. Does this help? Like, is this starting to make some sense? Get some intuition? Any further questions? All right, so before I actually launch into the proof of this theorem, this is a good time for me to pause for a few minutes, and I will take any questions that you have. So before we get into the proof, let me just draw out the whole complexity hierarchy so that you kind of see where all of this sits in the context of things that we've done so far. So the comment made was absolutely right that sigma I SAT is a special case of QBF, and assuming the theorem, we know that sigma I SAT is a language in p-space. Indeed, what this means is that the polynomial hierarchy entirely sits in p-space, and it's like a scaled down version of p-space. So let's go back to our sort of original picture of you have p and you have np and you have co-np. Then what you get here is this is sigma 2 and this is pi 2, and then containing all of this is sigma 3, or containing all of this is sigma 3, and then this is going to be pi 3, and all of this is the polynomial hierarchy. But all of that basically sits, it's much bigger, so I'll just draw it like that, and all of this is p-space. Sorry, this is a bit confusing, but so this is the polynomial hierarchy, which is like a scaled down version of p-space. It's fixed number of quantifiers. P-space is just arbitrary number of quantifiers. The number of quantifiers may depend on the input size. Here, the number of quantifiers doesn't depend on the input. Okay, any questions? Hopefully, this This makes sense. It is not the most easiest definition to digest, so it is something that one has to look over multiple times to understand. Questions?
I was feeling kind of nervous when we first started this. I didn't know, what is this polynomial hierarchy, existing in? But now that I know that it's in P space, I feel a little bit better.
Yeah,
about this whole picture.
I think it helps to sort of put it in context of what you've already seen, right? So you've seen these complexity classes. Yeah. Again, P space is something that we kind of intuitively understand because we're used to thinking about time complexity and space complexity. But even then, you may have noticed that when we were doing lots of things with space complexity, like Savage's theorem and NL equal to Cornell, a lot of the arguments would have been quite unfamiliar because they don't talk about runtime, they talk about space, which behaves differently. And now we have yet another, almost like another resource, like alternation.
Interesting.
So it's like a different dimension of things to look at. So you have time, you have space. There's even a more formal notion of alternating Turing machines. But there's this notion of alternation, which is now part of this entire picture. Okay, let's go ahead and let's prove that sigma I sat is sigma I complete. So, we proved by induction on I. And what I will do is, let's use definition 2 for sigma pi. What is definition 2? Just to recall, definition 2 was in terms of this alternating certificate viewpoint. The alternating certificate viewpoint, so that X is an L if and only if there exists a U, so that for all U2 there exists a U3, so on and so forth. Okay. So the base case, which is I is equal to 1, and this is just saying that SAT is NP complete, and that's just the Cook-Levin theorem. So SAT is NP complete, and tautology is co-NP complete. So this we knew, or whatever, either way, co-NP complete, both the same. Now let's do the induction. Let's assume for I, assume the theorem for I. So when we assume, so we assume the theorem for I. Now let's consider some L in sigma I plus 1 P. Okay, now we need to prove that L reduces efficiently to sigma I plus 1 SAT. Okay, so let's just use the definition. Okay, so using the definition of sigma IP, which was definition 2, we know that there exists a Turing machine M that runs in polynomial time, and a polynomial q such that x is in L if and only if there exists a u1 so that for all u2, so on and so forth, going all the way up to ui plus 1, mx u1 u2 up to ui plus 1 accepts, and the size of ui is at most polynomial in the input length. Right, so this is just saying, I'm just rewriting the definition. So there exists this polynomial time machine such that if there exists a u1, such that for all u2, so on and so forth. Okay, so now let me use this to define an other language called L prime. So I'll say that L prime is actually the set of all pairs u1, u2, such that for all u2 there exists u3 going up to ui plus 1, mx u1 u2 up to ui plus 1 accepts. This is now I alternations. Therefore, L prime is basically in pi I, right? Because it's I alternations of some polynomial time Turing machine. So it's just saying that if you took the certificate and you made that part of the input, so now you need to, it's like saying that all pairs such that for all u2 there exists a u3, so on and so forth, that language is going to be in pi I. And by induction, L prime reduces to pi I sat. Okay, now let's look into what this means. It means that there exists a polytime reducer R that, given x u as input, x, I'll call it u1 as input, computes a formula, I'll call it pi x u1. It computes some formula, pi x u1, and I'm just gonna switch the notation v1 v2 up to vi, such that x u1 is in L prime if and only if pi x u1 is in pi I sat. Okay. So this is just saying that by induction, L prime. So what is L prime? L prime was a language where I simply took out the first quantifier and I just sort of appended that to x and said, okay, let's look at pairs x u1. And if I want to determine if the language of x u1, that language is actually in pi I, because they're I alternations. If you were to go back to NP, that language would be in P, which actually is like the 0th version. But in general, when you take out the x and the first part, which is like the initial there exists, like think of that as a certificate. When you club those together, the language of x with the u1, that language is in pi I. And by induction, there is a reduction to pi I sat. Now, what does that mean? It means that there exists a polynomial time reducer. It's a polynomial time procedure that if you gave it x u1, it will basically output, given as input this, outputs or computes a formula phi x u1 such that phi x u1 is in pi I sat. I'm just stating what it means for this, for there to be a reduction. So let's kind of sort of let's open up this procedure. We'll say x is an L if and only if there exists a u1 such that x u1 is an L prime. But x u1 is an L prime if and only if phi x u1 is in pi I sat. So x is an L if and only if there exists a u1 such that phi x u1 is in pi I sat. Okay, so I'm going to write this out, and then ask me if this makes sense. So x is an L if and only if there exists a u such that for all v1 there exists v2 all the way going up to vi such that pi x u of v1, v2 up to vi is true. This is actually itself, there is a quantification over the formula. I mean, the formula is itself a function. It's some function of x and u, right? It's a function of x and u. Now, what we want to do, what do we want? Like, let's sort of step back and see what we want. We want to compute some C. We want to compute a formula C. So given x in poly time, we want to compute some C, and C is going to have, I'll just say it's z1, z2 up to zi plus 1, such that x is in L if and only if C z1 zi plus 1 is in sigma I sat. This is equivalent to saying that there exists z1 so that for all z2 up to zi plus 1 C is true. So it seems that we're almost there, except this formula is not okay. So the formula is a function of both x and u, whereas in this setting what you want is for the formula to be only a function of x. Okay, so here what we want is for the formula to be a function of x. So C is a function of x. That's what we want. Instead, we get a formula that is itself a function of not just the input, but also the first thing that we're taking the existential over. And so now what we need to do is figure out a way of getting from this part where phi xu can be converted to something that is only a function of x. Now for this, we're going to actually have to invoke the Cook-Levin theorem, and it is possible. I don't want to do it right now because I think it's a good time to end the lecture. And in the next lecture when we come, we'll complete this proof, and then I will also tell you why the two definitions of the polynomial hierarchy are equivalent. And that will probably wrap up our discussion of the polynomial hierarchy. So I'll end here and take any questions.